Hello everyone, and welcome to my talk for World Space Week 2020. So I'm Hazel, I'm an undergraduate student here at the University of Birmingham, and I'm also AstroSoc Secretary. But unlike my other friends in AstroSoc giving talks this week, I'm not a physicist. I'm a geologist. So I guess my understanding of satellites is somewhat different. But today I'm going to talk about something I do study, and that satellites do have a potential to have a positive impact on life in the future. And that's the potential for us to use them to deliberately change the climate, a process known as climate geoengineering, in response to climate change. I'll explain exactly what I mean by the term geoengineering in a minute, but first, a quick background so that we're all on the same page. The Earth's climate is warming, right? This is a graph showing the temperature difference from the 20th century average, and the positive trend towards the future is quite obvious, right? So if this is the future, what kind of temperatures are we looking at, right? What kind of temperature rise are we expecting from climate change, and what is going to come from that? Well, there are several different scenarios, and these are expressed by the Intergovernmental Panel on Climate Change as RCPs, or Representative Concentration Pathways. So these are kind of the different pathways of temperature increase that would follow depending on different concentrations defined by the concentrations of atmospheric CO2. So this, the bottom one is RCP 2.6, which is kind of the lowest CO2 atmospheric concentration prediction, and this is with a higher atmospheric CO2 concentration. And you can kind of see that we're expecting a warming from somewhere between sort of 0.5 degree to 8 degrees, but also looking at this, so this is the uncertainty, this kind of shaded area, maybe even up to 12 degrees, right? And with that temperature change comes all the effects we know about, right? So we'll be thinking about things like increased ice sheet melting, glaciers melting, which will lead to sea level rise, also changes to kind of weather systems, so more extreme weather, things like more droughts, more forest fires, right? It's a lot of impacts, and it's not necessarily seeming like an optimistic future. So another question that could perhaps come of this is there a way for us to have this CO2 concentration predicted here, but in some way mitigate against the negative climate impacts that would come with this? And that's where geoengineering comes into this, where it becomes potentially a part of our future. But firstly, what is geoengineering? So geoengineering is defined as the deliberate and large-scale intervention in the Earth's natural systems to counteract the effects of climate change. So fundamentally, this is about humans intentionally changing the Earth's climate in a way that would mitigate some of those negative impacts of climate change. It might, I guess, sound a little science fiction, right? The idea of changing climate on a planetary-wide scale, something that big. But it's important to remember humans have been unintentionally changing the Earth's climate for hundreds of years through our CO2 emissions. This is the root of the climate crisis, right? Climate change is due to our CO2 emissions, and that has caused a change in climate without meaning to. So what if we kind of turn to the climate problem but with some intent and with modern day technologies, and we thought, what if we tried this time to change the climate, but to change it in a way that would mitigate some of these potential negative and harmful impacts of climate change that we've been talking about? And that's kind of what I'm going to talk about today. So firstly, I guess the main question from this is, could we do it? Could we change the climate on a planetary scale? And the answer to that is probably yes. And I'm going to talk today about a few of the methods that we potentially could do that by. But I also hope on hearing this that the other question that is in your head is, should we do this, right? Is this something that we should be doing? And that's where I'll end this talk. After I've spoken a bit about how we could do it, we'll think about whether it really would improve life. Right, so in general, the climate is warming because more of the incoming solar radiation from the sun is being trapped by the increased concentration of CO2, right, and other greenhouse gases. So if there was a way for us to reduce the amount of solar radiation heating energy coming into the Earth by an amount comparable to the extra amount being trapped by these greenhouse gases, we could probably maintain a temperature profile similar to today, right? So if less energy is coming in, but more of that energy is being retained, but if those increases balance, we could probably have a similar world. Obviously, the question from this is, how do we stop? How do we change the amount of solar energy coming from the sun? So this is what the first branch of geoengineering is about, solar radiation management, thinking about ways in which we can affect and reduce the amount of solar radiation reaching the planet. So I'm going to kind of explain a couple of methods that have been proposed to do this. This is not all of the methods, but just a few of perhaps the most common ones. So the first one is known as space reflectors. So these are essentially mirrors in space, right? So these are kind of giant solar sail-like mirrors placed up in space, and with the aim to reflect sunlight away from the Earth back into space before it reaches the planet. So this kind of isn't a new concept, right? These kind of things have been applied to other planets for quite a while. So in the 1980s, this was spoke about a lot in terms of thinking potentially, theoretically, could humans live on Venus in the future? And these kind of methods have been needed there. But as the climate change kind of debate and problem became bigger, these have now been applied to the Earth. So kind of to maintain these sort of satellites, these giant mirror, essentially, satellites in space, the ideal place to put them is somewhere where they're held by a kind of gravitational equilibrium. So these are kind of points in space where the gravitational pull between things like the sun, the Earth, and the moon is balanced, so that the satellite could maintain its relative position. These are called ground points, and this is kind of point L1 here is where these kind of satellites would be set up. So this is a place where a space reflective satellite would maintain its position between the sun and the Earth, and this incoming solar radiation could be reflected away from the Earth before it reaches us, thus cooling the planet. So, you know, there's less incoming radiation, the planet would be cooler. So this sounds quite feasible, right? There's nothing that makes this sound impossible. So this is perhaps one way that we could cool the planet and mitigate against some of these temperature effects, even in a high CO2 world. Another potential way of doing this is something known as albedo enhancement. So instead of thinking about putting artificial reflectors up in space, this thinks about increasing the reflectivity of the planet, making the planet more reflective, so it itself reflects away some of the solar energy. And this is kind of based on a currently observed phenomenon that satellites are seeing currently. So this is from a NASA Earth Observatory satellite, and it's a sea just west of Europe. And I'm sure you can all see these kind of thicker, white, more bright, more reflective pathways crisscrossing the ocean here, right? And so these have been found to correlate with shipping lanes. Yeah, satellites have been observing this for quite a while, and people have researched into it. And these are where shipping lanes are going. And what's happening here is, as these ships are traveling along, they're releasing emissions, obviously, and this contains lots of kind of small pollution particles. And so when these pollution particles go up in the atmosphere, they're acting as condensation nuclei for clouds. So for water vapor in the air to condense and form clouds, it typically has to do it on some sort of surface, a condensation nuclei. So this could be things like salt particles, pollution particles, just other small atmospheric dust, atmospheric particles. So in these lanes, there's quite an abundance of these nuclei. There's a lot of pollution released by ships. So these clouds are forming lots of little droplets, lots of things as condensation on individual nuclei forming small particles. And these very small particles reflect a lot of energy. So the energy is coming in, it's being reflected around a lot, interacting with these small particles, and therefore a great amount of it is being reflected back up into space, and therefore increasing how reflective these clouds are and how much this is picked up by satellites. In contrast, in the kind of areas between these, where there are not lots of ships, these condensation nuclei are quite sparse. So instead of lots of little ones, there's very few. So what happens here is the water vapor condenses on those, and other droplets are then condensing on top of the already formed droplets. So you get clouds made of very fewer, bigger water droplets. And obviously these fewer droplets, there's less scattering of energy as it's coming in, so there's less chance for it to be reflected back into space, and it appears less bright, less reflective. So this is not a new effect, right? Satellites and people have been observing this and analysing this for a while. But a paper published this year kind of looked to quantify this mathematically, right? And what they found was that pollution effects similar to this, so ships and things and brightening clouds, is responsible for reflecting away about 1 watt of solar energy per square metre of the Earth's surface. That doesn't sound a lot, but in contrast, kind of the increased heating due to anthropogenic greenhouse gas emissions is currently increasing the heating by 3 watts per square metre. So essentially what this is saying is that this unintentional effect of pollution, it could be currently already counteracting up to 1/3 of our emissions, right? And this paper goes on further to say that if this effect was not happening, the planet would already be 1 degree warmer. So essentially this effect is already cooling the planet. And I guess firstly, this highlights one of the issues with solving climate change, with the climate problem, is it's also complicated and interconnected. There are so many effects that feed into each other and lead to things we wouldn't know about, things that no one's considered perhaps when it started, right? And secondly, it also shows the issues with kind of the rapid emissions reductions, perhaps, that maybe even changing something like that, which would seem in theory wholly positive, could have unknown and unexpected negative effects. But in terms of geoengineering, this kind of nice observation by satellites has led to the proposal of a new type of geoengineering known as marine cloud brightening. So this is where people are going to aim to deliberately enhance this effect. So instead of obviously using pollution, because that seems a bad idea, they're thinking about other condensation nuclei they could use. And what they've settled on is salt particles. So here is a theoretical kind of marine cloud brightening station, how these might look in the sea. And what they do here is pump seawater up into the air. This contains salt crystals, because the sea is salty. And these are then in the atmosphere, and these act as condensation nuclei, allowing the clouds to form with multiple small water droplets, which then scatter more light, are more reflective, cool the planet. So again, this appears perfectly feasible, right? This seems another way that we potentially could cool the planet, this time by making clouds more reflective due to the addition of kind of spraying salt water into the atmosphere. Nothing too crazy. The final kind of topic about the final type of solar radiation management I'm going to talk about is something a bit closer to what I study as a geologist, because it's inspired by volcanoes. So this down here, this is Mount Pinatubo, and this is when it was erupting in 1991. So as you can see, during this, it was a very large eruption. A large cloud of ash and dust and gases was erupted up into the atmosphere. And you can also see by this temperature, this graph of global temperature, that in the kind of 2.5 to 3 years following the eruption, there was a marked decrease in global temperature of kind of just over 0.5 degree, right? And so this occurred because during that eruption, alongside the ash and dust, which were kind of fairly quickly removed from the atmosphere, it also erupted lots of gases, particularly sulfur aerosol particles, and these rose up to the stratosphere, as shown here, where they have a fairly long residence time. So these kind of remained in the stratosphere for the several years following the eruption. And as you can see over here, again, these form a kind of aerosol cloud, and once again, incoming solar energy is scattered by interacting with these particles, and more of it has the potential to be reflected back out to space. So kind of the potential for geoengineering for this is to artificially increase and to artificially put aerosols into the stratosphere. So we can't be relying on volcanoes, but this kind of system that's been argued, we probably use a balloon similar to a current weather balloon. These would be sent up from ships, and when they reach the correct level in the stratosphere, they would release aerosols. These would then form this kind of cloud, similar to after an eruption, and continue to reflect away sunlight, cooling the Earth's temperature. The kind of issue with this is the aerosols that are from volcanoes were typically sulfate aerosols, and these have been shown to have a negative impact on ozone. So they enhance ozone depletion, which is obviously negative. We need ozone to protect us from harmful radiation. So current science and research into this is kind of focusing on choosing the correct aerosol particles that will still scatter the sunlight, but which are the least reactive, which don't affect and interact with ozone reactions or other chemical reactions, and just remain kind of unreactive and inert in the atmosphere. But again, this is seeming kind of perfectly plausible, right? Nothing too mad. This is technology we could do, we have. So maybe this is all kind of seeming quite positive, right? It could be considering we've found the solution. But, you know, obviously these are good methods. There is potential here to stabilize and reduce global temperatures. And in a way, this could and likely would mitigate against these climate effects, you know, reduce ice cap melting, which would reduce sea level rise, etc. But I hope you can see by just glancing at this slide that there are a lot of potential drawbacks. It is a balance, right? So one of the things to think about is a temperature increase, although the most common and the most talked about, isn't the only problem with a high CO2 world, right? Other things will come from this as well, such as ocean acidification, and none of that kind of thing will be in any way affected by these geoengineering methods focusing on just reducing global temperature. Also, as I just spoke about with the aerosols, they may have an effect on things like ozone depletion. There are unknown reactions perhaps that we don't know about and haven't fully modelled or comprehended, so further study is needed. There's also heating, and solar heating has a large effect on global precipitation, on the hydrological cycle. So there's obviously an potential impact that by changing this will affect global rainfall and global rainfall patterns, and obviously water scarcity is a big problem for plenty of places in this world, so this needs to be considered. A reduction in solar energy may also impact crop growth and would also mean less energy is available for solar power, which may be needed in a decarbonised future. But I guess as a more kind of fundamental problem to geoengineering is it's very difficult to predict the outcomes of these kind of schemes without full-scale tests. And by full-scale tests, we mean kind of planetary-wide tests, essentially doing it. So it's very difficult to understand the full climate system, right? I think you saw on the first graph just how large the uncertainties were of our predictions for the climate future and temperature ranges. The climate system is unbelievably complicated. It's an entire planet. And so we can run as many models as we want, and we are getting better and better models and trying more and more to understand all of these systems. But it's very difficult to predict with a good degree of certainty what will happen. So perhaps the only way to fully test these out would be to set up some of these schemes and see what happens. And obviously the issue with that is if a negative effect is then discovered, with a lot of these we cannot stop their effects immediately, right? So if you put stratospheric aerosols up there, these aerosol particles have a certain residence time in the atmosphere. It takes a certain time before they naturally fall out the atmosphere, and there's no way to remove them until then. So if we were to find a negative impact, there isn't much we can necessarily do to stop that immediately. So in several ways it is a commitment, it's a gamble. But also with these schemes, rapid warming would occur if or when it was stopped. So if we're using these to reflect away solar energy, but the CO2 concentration is still the same, the second that reflector, say your space mirror kind of satellite is removed, the second that happens, then temperature rise will start, and it will be quite rapid. And the problem is rapid changes are the sort of thing the climate system, kind of ecology and environmental things cannot cope with. This is kind of when you lead to kind of mass extinctions, right? If a change is gradual, things can adapt, but rapid changes tend to be environmentally bad. So that is another risk. If we kind of delay it with these artificial systems and don't maintain it, then rapid change could occur. And kind of this final bullet point of moral, ethical and geopolitical issues is not kind of stuck on here because it's one small irrelevant thing. Instead, that's a very large part of this problem, and is what I'm going to talk about at the end of the talk. But first, if we kind of return to the first point, that there are other impacts of a high CO2 world that cannot be mitigated against purely by a temperature decrease. Think, what if we kind of attack the source of the problem, right? So the planet is warming due to increased emissions from human activity of greenhouse gases, particularly CO2. So is there a way to remove that CO2 from the atmosphere, right? Can we reduce the overall levels of CO2? And this is kind of the second most common branch of geoengineering, known as carbon geoengineering. So again, there are lots and lots of potential ways to do this, and I'm not going to explain them all, but I'll just focus on one, kind of the most obvious way, and think about how this might impact us. So in terms of what is the most obvious way to reduce CO2, well, can we just take CO2 out of the atmosphere, right? Can we directly remove it from the air? And the answer to this is yes, and it's already happening. So this is the Climeworks plant. This is a Swiss company that set this up in a power plant in Iceland. So this is a currently operating system in Iceland. And they've aimed, and they have created here, the world's first carbon negative power plant. So by taking a geothermal power plant, where energy is created through the heat from volcanic rocks, of which there's an abundance in Iceland, you've already this is generating energy in a carbon neutral way. So this is not releasing CO2. And by adding this Climeworks project, where they're taking CO2 directly out the air, this power plant overall has a net negative impact. This is essentially done, your ambient air with your CO2 in it is taken into this little machine. Here it's run through a reactive membrane. Reactions occur, so the CO2 gets trapped on that membrane, and the air without the CO2 passes out of here, and this is CO2 reduced air or CO2 free air, and it's continued back into the atmosphere. The CO2 is taken and mixed with water. So this is kind of creates carbonated water, essentially the basis of a fizzy drink. And this is pumped underground to a basalt formation. So the geological considerations of this are quite important, and you've got to choose the correct rock. So here basalt is chosen for several reasons. Firstly, because it's very porous. So this means it's got lots and lots of little holes in it. So this gives space for the CO2 and air mixture to flow, and there's room for it to be stored. But basalt is also has a high concentration of elements that react with CO2, so things such as calcium, iron and magnesium. And these undergo natural reactions with CO2 to form other minerals. So this is kind of a typical process which happens, but it's just being expedited through pumping concentrated CO2 in. And these will react, so you'll get your calcium and your carbonate will react, creating calcium carbonate kind of minerals and other carbonate minerals with CO2. And these will fill up the pore spaces in that basalt. So what you've essentially done here is you've taken it out the air, you've pumped it underground, solidified it in a rock, a kind of unreacted natural rock, and that is then stored away for quite a while, right? Sounds good, right? This sounds like a solution, perhaps, you know? We're removing CO2 from the air, that's a positive. And it is a positive, but the issue here is kind of one of scale. So this program, as I said, is currently operating, and in the last year, it removed about 10,000 tons of CO2 from the air. So this sounds a lot, but if you consider it in context, that's the same as the average emissions of 650 people in Britain. So that's probably smaller than, say, your secondary school. You know, it's not very large. And obviously, if we want to overall reduce the concentrations of CO2 in the atmosphere, you know, have a net decrease, we need to not only be meeting emissions but exceeding them to reduce this. And this kind of thing just isn't possible at the minute, right? The scale of the amount that you can remove from the air is just in no way comparable to the amount we're taking out. And there are other ways proposed to do this, right? People have been thinking about other ways we can remove CO2, maybe enhancing the amount of CO2 that the ocean absorbs, thinking about enhancing that process and other things. And all of these things perhaps together contribute a bit of a solution, right? This is a way to remove some of it, but in no way it doesn't solve it, right? And I guess what I've really hope I've illustrated up to this point in the talk is that we could do it, right? There are plenty of ways that we could modify climate. And nothing I've mentioned today is kind of science fiction like technology, right? I've not talked about anything completely unfeasible. I've not talked about anything that isn't conceptually simple and with a little bit of, you know, further research and thinking about developing it and deploying it that couldn't be achievable. So the answer to the first question of the talk of could we modify the climate is kind of most likely yes. You know, these things are looking feasible. So then we return to the second and possibly the more important question is, should we modify the climate? Science does not exist in a bubble, right? It's not about just proving that we can do it and fixing the problem, right? There are other implications that need to be considered about like moral and ethical and political and feasibility questions, and that's what we're going to talk about now. But I think the first thing to emphasize is that geoengineering is not a new topic, right? It sounds it. It's kind of very new that it's being talked about. It's very new that lots of people or more and more people are knowing about it, but it's not new science. It's been talked about kind of quietly and politically for quite a while. So in 1965, the then US President Lyndon Johnson was given a report by his climate advisors talking about the possibility of deliberately bringing about counteractive climate action, including the possibility of raising the albedo/reflectiveness of the planet. Right, so this is the things I've just been talking about. This is what I was talking about marine cloud brightening earlier, of making clouds more reflective to make the planet more reflective. So why is geoengineering just becoming public? Why are we just talking about this more kind of 50 years after these things were beginning to be suggested by scientists? And one of the main reasons for that is something known as moral hazard theory. So the problem with spreading it on science communication is often these things are not fully considered in niche. So the knowledge that geoengineering is possible, if lots of people know this, then there is the very likely potential that the understanding of the limitations of geoengineering will not be fully considered. So people will learn about geoengineering, but they will not truly understand the limits of it, and it will kind of be inaccurately perceived as a solution to climate change. We have found the solution, right? And then obviously, if this is the belief, if it seems that we either have a solution or that by inventing these technologies, we have the possibility to, in the future, invent a solution, climate change suddenly appears less of a serious threat. And obviously from that, the commitment to taking drastic measures to reduce emissions weakens, right? There's no point doing drastic things if we're going to have if we have the solution or are going to have the solution. And then the problem with this is obviously geoengineering is not a solution to climate change. I hope that's come across in this, but it's not a solution, right? There's only so much CO2 we can remove from the air. There's only so much sunlight we can reflect back to space before that has a negative impact on the planet. There's only so many aerosols you can put in the air, right? These things are not going to solve climate change if emissions continue the way they are. The commitment needs to be first and foremost to emissions reduction, as is well known now. So that, I guess, is the moral hazard of geoengineering, that people, if they talk about it, if it's widely reported, think climate change is not a threat. And we still end up with a climate catastrophe. Because the people kind of studying this, the scientists involved in geoengineering, a lot of their views is that this is not in no way a solution to climate change, but perhaps could be used as a kind of stopgap measure, a way to mitigate these negative impacts whilst we undergo the necessary processes to transition to a less carbon intensive future. So whilst we're setting up and implementing the infrastructure needed for renewable technologies, whilst we're building things that work for this, whilst we're making these more efficient, we could use perhaps some of these geoengineering methods to keep the temperatures stable, to work on making the climate crisis less bad. You know, some of the impacts we're already beginning to see, to make these less bad whilst we can transition to a sustainable low carbon future. Right? So let's say geoengineering gets talked about this way, right? Let's say everyone does it with the understanding that emissions reduction is still foremost. This is not in any way the only issue of geoengineering. A lot of issues still remain, and these are highlighted kind of on this slide. So firstly, the problem is with who would do it, right? So the thing with these solutions is they're very cheap. Now, obviously by cheap, they're still extraordinarily expensive, but these are kind of, doing some of these solutions would require a budget comparable to the military budget of large countries, the healthcare budget of a large country, right? And so by taking that kind of approach, it means that countries could decide to do this. A well-off country could decide to do this themselves as a country, a single place. And that leads to the second question: for whose benefit would they run this scheme? So schemes like this, which impact the entire planet's climate, are obviously going to have an effect on everyone. So these need to be, the benefits need to be thought about, right? It can't be about just doing something that improves their climate, the climate of this country. It needs to be thought about how could we ensure these solutions include the voices of those who are most vulnerable, those who are perhaps least represented in these conversations, but how could it have a globally positive effect? How could everyone benefit from this, rather than one country focusing on the positives for them, which would have unintended or kind of unconsidered negatives for other countries? And that leads on to the next one: who would regulate it? So obviously, to do this successfully, to change the climate of an entire planet and the entire Earth, we would need agreement between all countries, right? This would need to be a global and universal commitment to this, with the considerations kind of considered for everyone. And so who would be in charge of this? Who would sign, you know, who would ensure that countries are keeping their bargain, that this is a positive for everyone, that we're working about this in the correct way? And then also, how would the long-term stability and funding be guaranteed? As I mentioned earlier, obviously if you rapidly stop one of these solutions, at least a rapid changes in climate. So what would need to be done before these schemes is that people understand and are committed to funding them in the long term, to running them stably, to thinking about how the setup will be managed, the maintenance, and then how we would stop these solutions in the future, how that would happen without climate catastrophe. You know, we can't be building these and then an election happening and then suddenly it's stopping. You know, this has to be a long-term and agreed commitment. And I think perhaps less optimistically, the response to a lot of the current crises and to the climate crisis up to today has shown that there's very little political willpower for this kind of global, universal, overarching aims, you know, everyone aiming for something that is universally beneficial, even if that perhaps means that for some countries it's less beneficial, or that the focus needs to be on those who are more affected by this, perhaps those who are less well off. And so this is a significant problem with geoengineering, right? Is it needs to be done fairly and equitably, and it's difficult on a global scale. It's difficult to have the political willpower and organization for those kind of things. And finally, the question kind of remains, is it morally correct, right? Do we have the right to try and change the climate? Like, obviously humans have changed it unintentionally, but is it fair for us to turn and deliberately try and change this, to deliberately set about to modify the natural world? But the flip side to that coin that some people discuss is also, on the other hand, is it morally correct for us not to do this? Is it correct for us not to try and fix our problem? Would it be correct for us to have the technology, or the potential to have the technology, and let this crisis happen anyway? Obviously, everything that's happening on this planet affects species way beyond us. So would it be right for us to say, to have knowledge of how to do this, but let the ice caps melt, let the polar bears go extinct, right? Or would it be more correct for us to do it? This is a very difficult question, right? And I think with all of these questions here, I don't know the answer, right? So this question remains, is should we modify the climate? All I can express is my personal opinion. And I am personally not sure if this would be a sensible idea, but it's difficult to know, and nobody really knows. This is the current question. This is the current debate about this. You know, we're looking this year for World Space Week about about how satellites improve lives. Well, this is a point where perhaps the question would instead be, do satellites improve lives? we'd be thinking, is this in our future a net positive? Nobody knows, right? And so this is the question, this is where it ends. So in general, thank you for listening, but also if you want to know any more about this, these are just kind of some things I looked at whilst writing this talk and that I found interesting. There's a couple of TED Talks quite short on this, which I found really interesting, both by guys called David. This is a book by Oliver Morton all about it called The Planet Remade, and I found that a really fascinating read. And finally, the University of Oxford has an Oxford Geoengineering programme, and they have a blog. And on this blog, it's written by lots of people from lots of different perspectives. So there's perspectives of geoscientists, of people who study the economy, of social scientists, of politicians. So this is kind of a really good way to consider something that will affect everyone from a lot of different perspectives. It's not just in this way about science, about space science, about planetary people, about like climate scientists. This is a thing that involves everyone, and this is a really good place to look at it. So thank you for listening, and if you've got any questions, put them in the YouTube comments below and we'll try and get back to you.